Given is the following digital circuits with the two inputs A and B. The circuit has a 3 nanoseconds delay at each one of the gates. Draw the timing diagram for Y. We have the signals of A and B given. So in the first 10 nanoseconds, A is 0 and then it becomes 1 and then 0 and 1 again. For B it is 0 and 0 and then 1 and 1. Now the most important thing here is to go step by step. And I mean you go gate by gate. You start with the first gate that gets the inputs and then you build on it. So for example here, this gate comes first. It will have the propagation delay before this gate right here. And that is why you start with this one. So before I start with Y, I need to draw the output of this one, which is simply a NOT, since this is a NOT gate, which we will do right here. So we need to draw a NOT first. Let me go ahead and change the color, by the way, because I can't see anything. There we go. This looks much better. So here we need to draw the A NOT signal first. And because of the 3 nanoseconds delay, this gate right here, the NOT gate, will not get a signal in the first 3 seconds. So in the first 3 nanoseconds, 1, 2, 3, the signal right here will be undefined basically. Now what happens after that, after 3 nanoseconds? After 3 nanoseconds, A will be inverted basically. So there, it's a 0, and down here, it will become a 1 basically. And now starting from here, after 10 nanoseconds, it will be inverted again. However, there's a 3 nanoseconds delay. So the gate will take 3 nanoseconds, 1, 2, 3, until it realizes that the input should be inverted. Only after 3 nanoseconds, after 10 seconds, will the input be inverted. And now it continues. And here at the mark of 20 nanoseconds, the same thing happens. It should become a 1. However, because of the 3 nanoseconds delay, 1, 2, 3, it will become a 1 after this much time. Here the same thing happens again, so we need to count 1, 2, 3, and after that it will become a 0. Now we have A NOT and B being XORed. This right here is an XOR gate. And we have one of the inputs is B, and the other one is A NOT. For all of you who don't know, an XOR gate basically is like adding 2 binary numbers. So in this case, we need to look at A NOT and B and add them up. And based on that, we will have an XOR output signal that is based on both of them. However, we can't forget that there is also a 3 nanoseconds delay right here. So we need to keep that in mind. As a quick reminder, I'll write down the XOR truth table for 2 inputs. So now we can continue with the timing diagram of Y. Y takes in A NOT, so we need to look at this signal right here, and B. Now for the first 3 nanoseconds, we'll not get any signal from A NOT. That is why here there will be nothing, basically. Now it looks like the gate can start working, but we can't forget the 3 nanoseconds delay. So here at this point, Y will get the signal and it will need 3 nanoseconds to process the signal. So 1, 2, 3, which makes the first 6 nanoseconds in this case useless without any signal. Now we can start checking what will be outputted. A NOT is 1 right here, and B is 0. And 1 plus 0 is 1. That's why we will have a 1 here. Now, this will last until this time point right here, as you guys can see. So I will go on until here. Now, starting from here, we have 0 plus 0, which should be 1. However, it will take 3 nanoseconds, the XOR gate, to react. That is why after 1, 2, 3, it will go down. It will stay 0 and 0 up until this point, until 20 nanoseconds. And here we have 0 and we have a 1 above, as you guys can see here. and therefore the output should be 1. However, only after 3 nanoseconds will it react. So 1, 2, 3, and here it will go up. Now instantly after it goes up, we have 1 XORed with 1 here, which is 0, as you can see in this truth table. However, it will need 3 nanoseconds to react. So right here it goes down and continues until this point right here. Now here we have 0 and 1 again. So the output should be 1, but again it will take 1, 2, 3 nanoseconds, and then it will go back up to 1. And by the way, you guys, as you can see, this right here shouldn't be there, and that is what we call a glitch in a timing diagram. It only happened because of the propagation delay. If there was no delay, in a perfect case scenario, it should be a 0.